why does my digital voltmeter read 4.3 volts, but my analogue moving coil voltmeter reads 1.5 volts? This simple circuit with two 10 kilo ohm resistors in series and a third 10 kilo ohm resistor in parallel is a useful one for a practical or demonstration to show the ideal properties of a voltmeter. I've set my power supply to 8.6 volts, and before we do any measurements, let's see if we can predict what each of the potential differences would be across the resistors. We would predict that the top resistor, which is in a branch on its own, would get all 8.6 volts, whereas the two resistors in the bottom branch, because they're identical, would get half of the potential difference each, which would mean they would get 4.3 volts each. So let's check that first with the digital multimeter acting as a voltmeter. And if we try across the resistor which is in its own on the branch, we're expecting 8.6 volts, and we get 8.6 volts. So let's move the voltmeter and connect it across one of the resistors in the bottom branch, and as expected, we get 4.3 volts with the first one of those. And so let's move it to the third resistor and see if we also get 4.3 volts, and indeed we do. So now let's remove the digital multimeter, which was acting as a voltmeter, and instead use a moving coil voltmeter. And connecting that across the top resistor, we're reading about 8.2 volts, which is not too bad for this almost antique voltmeter. So let's now try moving the voltmeter and measure across one of the resistors in the bottom branch. And so we'd expect 4.3 volts, but what's going on? It's reading about 1.5 volts. So we were expecting 4.3 volts and we got about 1.5 volts. So let's move the voltmeter and connect it across the other resistor in the bottom branch and see what we get. And that one, we're also getting about 1.5 volts. But how can that be? Because they've got to add up to the 8.6 volts of the power supply. I like to pose this as a puzzle to the students to see if they can work out what's going on. So then I suggest, well, let's check with the digital multimeter and see what that says. And that's saying 1.2 volts. So maybe now we should move the digital multimeter and see what it says for the other resistor in that bottom branch. And now that's saying 7.4 volts, which is a bit more reassuring because 7.4 plus 1.2 adds up to the 8.6 volts. So somehow, having the moving coil voltmeter there is changing the circuit. To prove this, let's try unplugging the moving coil voltmeter with the digital voltmeter plugged in. And when we do that, the digital voltmeter returns to the 4.3 volts that we were expecting. Dropping in a few hints, I like to see if my students can work out what's going on. A useful way of thinking it is that the moving coil voltmeter must have some resistance, so when it's connected there, we've effectively got another resistor in parallel. So let's see if we can measure the resistance of the moving coil voltmeter by using the multimeter as an ohm meter instead. So I need to change the setting on that to measure kiloohms and connect it directly, and we can see that its resistance of the moving coil voltmeter is about 2000 ohms or 2 kiloohms. Now let's do some calculations to see if we can predict the expected potential difference across that resistor and see if it agrees with what we actually measured. So first of all, let's combine the 10,000 ohm resistor and the 2000 ohms resistance in parallel with it from the analogue voltmeter and see what the total resistance of those two is. So for that, we'll use the equation for resistors in parallel. And when we work that through, that will give us a total resistance of 1667. Which means we could simplify our circuit to having one 1667 ohm resistor here instead of the 10,000 ohm resistor in parallel with the 2000 ohm voltmeter. And now we can see that this is like a potential divider circuit with a 10,000 ohm resistor and a 1667 ohm resistor. And if we apply the potential divider equation for the potential difference across this resistance, it will come out at 1.2 volts, which is pleasingly close to what we measured with the digital voltmeter. So the problem that we had was that when we added the voltmeter's resistance in parallel with the moving coil voltmeter, it significantly changed the total resistance because the resistance of the voltmeter was quite small, only 2000 ohms. So this can then lead to a discussion of the fact that we want the resistance of our voltmeter ideally to be infinite, but at least it needs to be very large compared to the resistance it's measuring across. I hope you found this video interesting and it's helped you to realise why we want our voltmeter to have as large a resistance as possible. Typically, the multimeters have a resistance of 1,000,000 or 10 million ohms, which means they work very well for a circuit like this. But they too would have limitations if we had very large resistances in the circuit.